All right, so we're streaming, and let me get me up there. So let me share screen really quick. Let's get this up. And this is going to start playing. Let me make sure that pauses. Okay, so there's that. So I just wanted to show you something in case you want it later. The first two videos in this playlist, I originally tried doing my lectures with PowerPoint last year when COVID started. And these were the very first two I did. And then it was so incredibly time consuming, I had to get away from it. But I think these first two videos, one of them is about 5 minutes and one of them is about 15 minutes. I think those two videos that I made were pretty good. My internet connection was a little bit slower, so I think these longer ones might not be that great. But we're going to go ahead and do this stuff now. But I just thought I'd give you these two, and I'll put a link in the chat. Let me see. Where's the chat? There it is. So I think those first two are short and good and effective, but you could tell me your opinion later. I think those ones were pretty good. So obviously, what are we going to do today? We're going to talk about center of mass. And so we're going to start by doing this point particle system, and then we're going to continue with the continuous distribution of mass. So it doesn't offend me if you want to be, crazy and go check out a Zoom and just go watch those videos and then come back, that's fine. Or if you want to just roll along and watch those videos later, whatever you feel like doing is good with me. So I'm not offended if you leave and go watch those and come back or stay here. All right. So that said, maybe let's start. Oh, I forgot to open the workbook. Let me do that just a second. So I'm going to start with the screen share, and we're in chapter 9. The last half of chapter 9 is talking about center of mass. So let me give you a page number, just a sec. Sorry about that. Whoops, wrong chapter. Page 43 in the workbook, page 43 in workbook volume 2. Okay, and I'll get that up here in just a second. Hope you had a good break. I know it's never long enough. Summer's going to be here soon. Final exam is going to be here soon. Oof. Get the right volume. There we go. So page 43 is what we're looking for. And let me get this over on this screen and do a screen share. Okay, today, computer. So sorry for the boring intro there, if you're watching this live stream later. All right, and so we want to go to, I think, page 43 is what I said. So we've got this center of mass strategy. So it turns out, before I even start going through this, you may say, why should I care about center of mass? Well, it turns out for a large number of objects, if you're, how about I just do this? So if I look at this eraser and I throw it across the room, I don't know if you noticed that, but it rotated as it translated. The rotation, generally speaking, will happen about the center of mass. So if we want to understand rotation in chapter 10, you could imagine that understanding center of mass is a pretty big deal. Also, if we talk about something swinging on a string, okay, this is the first thing I could find. But in this case, for this object that's swinging on a string, I was making some tea here. The idea is what matters is this thing goes about through space. Oh, I'm dripping tea everywhere. Geez. All right, let me get most of the tea out. Burning hot. It's all right. Who needs fingers? So when this object is moving through space, what matters is where the center of mass is located for gravitational potential energy. So again, we see two good reasons to talk about center of mass. As things fly through space, they rotate about their center of mass. So if we want to understand that motion, we need to understand where the center of mass is. And for objects that are swinging or rotating like this, the location of the center of mass is important for gravitational potential energy. So those are the two reasons I'm going to give right now for why you should care about this. All right. And both of them show up in force in chapter 10. So let's get back into there. And so it's going to be a lot like anything else. It's a pure math technique. Center of mass is straight math. However, the stuff they teach you in your math class, it's pretty good. Like you've done calculus with center of mass, perhaps, but it's just, yeah, it's insufficient, right? They don't do a great job. They do an okay job. So that's fine. That's not their goal. All right. So the first thing that you want to do is know the answer from a memorized list. For example, if I put a shape here, let me draw something. Let's say I have a piece of lumber. Most of you would have no trouble thinking, the center of mass is probably right. Whoops. The center of mass. Oh my gosh, come on now. Why is it not working? My annotation isn't working here. Oh my gosh. All right. Let's try again here. Let's do another shape here. See if it works this time. No. All right. I tell you what, geez. It's one of these days, Monday after spring break. Let's go old school. One of those days. Okay, imagine you have a piece of lumber here. Most of you would have no problem saying, well, isn't the center of mass right in the center? That's a good guess, assuming the lumber is approximately uniform mass distribution. Now, where this might get tricky is, what if you were looking at a side view and you didn't notice it, but what if the lumber got thicker from one end to the other, right? So this is obviously exaggerated, but you could imagine where a piece of lumber might be thicker at one end than at the other. And there we can't just guess the answer immediately, okay? However, for a lot of simple shapes, for example, a circle, assuming it's uniform, the center mass would be right at the center, a square right at the center. What about a triangle? And in particular, I want to talk about a right triangle. It turns out, the way I remember it is the center of mass is 1/3 from the fat end. So rather than try and do calculus and do all that stuff, you just say, look, split this into thirds. It's right there. Split this side into thirds. And so the center of mass would be right here, 1/3 from the fat end in each direction. So obviously this would work if our triangle was over here, right? 1/3 from the fat end would be over here. And so that's faster than doing calculus, just knowing those answers. And let's be clear here. We use square plates, circular plates, and triangular plates routinely because you could build up so many shapes out of these, or rectangular plates. I guess I could have gone even, right? Rectangular plates. We know the center mass is at the midpoint of the object. So just keep that in mind. If you don't have to do any math, don't do any math. Knowing the answer is the fastest way to get the answer for circles, squares, triangles. Let's get back in there. Maybe. All right, here we go. So now, I guess that's step 2 as well. Okay, so cool. Now, 1 and 2 kind of go together. Basically, if you could guess the answer and know you're going to be right, just guess. Okay, now what happens if an object is comprised of several known shapes? We could split this up, and let me just explain this with a picture, okay? So we're looking at bullet 3. We want to use this equation. Let me show you what this equation means on the board. So let's say I have 2 shapes. Let me get out a better marker here. Sorry, I'm a little discombobulated. I haven't lectured in a week. I'm just not flowing just right today. Come on. Having some trouble today. All right. So let's say you're making a deck or something, or some concrete object like this. And so you could imagine being a civil engineer and you need to make some kind of structure out of concrete. And maybe you want to support this structure. it would be very important to know where the center of mass is located, because if you put a support beam under the center of mass, right, then you don't have to worry as much about torques and rotation, chapter 12 stuff. And so there's another reason to care about this. But let's just call this object 1, and I'll kind of shade it lightly red here. And let's say this is object 2. All right. Now, you could say, could I use calculus to figure out the center of mass? You absolutely could, but you shouldn't. That would be a bad idea. One of the first things we're going to do with all center of mass problems is we're going to draw a coordinate system. So maybe I'll just say right here. And the idea is, I know the center of mass of this one. I'll call that x1, meaning the center of mass of object 1 in the x direction. I could do the same thing for this one. It's a triangle. It's a third from the fat end and a third. So the center mass of this one, sorry if that's not perfect, would be x2. And then the idea is to get the center of mass of the system, we just do this. We say, okay, I take the total mass on bottom and I do x1 times its mass on top and x2 times its mass. And the idea then is you're reducing this complicated problem essentially to 2 point masses. And so we will go into this more in depth, and I'll explain how you would plug in numbers in just a minute, but I'm just trying to give you a big picture overview. The idea is if you know where the center mass of a rectangular plate is, you call that x1 for this number. If you know where the center of mass is for this particular triangular plate, you could shove that in. If you know the masses of the plates, you could stick that in, and you would get the center of mass of the combined objects. Before we go ahead, maybe somebody could unmute, and I'll try and get you involved here. Where do you think the center of mass of the combined object is?
Leading towards the square or the rectangle.
Okay, good. We would expect it's somewhere between these two. And it looks like, now we don't know, but it looks like this rectangle has more mass than that triangle. So it's probably a little bit closer to there. So this is a good thing to do at the end of your center of mass problems, is just kind of think and use some reality checks and say, look, we expect it's probably somewhere between there. If you found the center of mass to be way over here, close to 0, you'd think, I think I accidentally put in a minus sign or something. Okay. So, all right. Usually the center mass is somewhere between all the center mass of the objects. So that's cool. All right. Any questions about this while we've got it up? All right.
Should we be
go for it.
Should we consider the y direction on this problem, or
you could, yeah. So absolutely. If you wanted to do the y center mass, you could then say, okay, this would be y1, and notice this would be y2. It's a little higher up, and you could replace all the x's here with letter y's and get the y coordinate of the center of mass. Absolutely. Does that help?
Yeah. Yes. Thank you.
Yeah. So you could do the same thing in 3 dimensions with the z coordinate. Yep. All right. So far this stuff's not too bad. Oh, and here's what's really crazy. You might not expect this, but look at this. I'll show you another neat way this could be applied. And we're going to do examples after we get this intro done. But what if you had a square plate and you need to drill a hole in it? So let's say you drill a hole in it right here. Well, if you wanted to, you could actually do this problem. This black marker is dying. Do I have another? Come on, please. Let's try this one. There we go. That's better. Sorry about that. You could actually say this is equivalent to a square minus a circle. And then in the center of mass equation, you get X center of mass total is equal to X1 M1 minus X2 M2. And you could subtract out, and then obviously we got to do the total mass on the bottom, which would be M1 minus M2. So you could actually do this same procedure if you view holes as being negative mass. So again, this shape would end up looking something like this. That's the same thing as viewing this circle as being made out of antimatter and the plate being a full solid square. So you take a solid square plate minus an antimatter hole, and you could actually quickly compute the center of mass without doing any calculus. Again, our goal is to avoid calculus unless absolutely necessary here. Calculus slows you down. Sometimes you need it. All right, so we will do examples with this later and see how the numbers work out. But so notice, if you have objects with holes in them, you could pretend that mass is negative. All right, so again, we'll do actual work problems later. Now, if we go through this checklist and you can't just guess or have it memorized or build it out of stuff that you do have memorized.
Mr. George said?
Yes.
I think you're sharing the wrong screen. You're sharing the solutions to chapter 9.
My bad. Thank you. Sorry about that. Click the wrong button. Thank you. Is that better? There we go. So, thanks. So, okay, let's rewind then. So if you can't guess the answer or have it memorized or just split it up into stuff that you do have memorized or use this negative mass trick, then we're going to have to use calculus. So here is the procedure for doing these things with calculus. And I think what we should do is maybe come back to the calculus in a minute, because as you can see, the calculus, we have to understand everything on this page. Okay. So let's start with some point masses and come back to this. All right. So we will come back to the calculus. So that said, let's start super easy and just make sure we got these. So let's start with 9.27. All right. Okay. So I'm going to go ahead and erase here. .27. Well, maybe I'll just try and blow this up a little bit. So he says each tick mark is 20 centimeters. The masses are 1, 2, and 3. Okay, so I'm going to assume this is the 1, this is the 2, and this is the 3. All right, and just so I can make this easier to label. All right, so there's this. So in this case, what is x1? Let's just get the x coordinate of center of mass right now.
So negative 20?
Negative, and that's what I wanted to point out. That's not quite right. Negative 20
times its mass?
Centimeters.
Oh, centimeters.
Okay. Yeah. So what happens here is center of mass, we got to keep the units in, and you'll see how it works out. All right, so just keeping you straight on units there. That's all. X2 would be positive 40, right? And then we better include the units. And then X3 would equal what? Negative 60 centimeters. So what did we see here? Plus minus signs matter, units matter, and you may have noticed there's a coordinate system. Notice we've defined an origin. So all center of mass problems need to have some kind of origin. If you don't draw your coordinate system, you're going to get a number, but you won't be able to express that number to anyone else and have it mean anything. So you have to draw a coordinate system, worry about your plus minus signs and your units. That said, let's see what we get here. When I plug in the numbers here, whoops. All right, and so Let me clear those annotations off. So here's the numbers we plug in. And notice you get kilograms in the basement, kilograms in the numerator in each term. The kilograms are going to drop out. And we get units of centimeters here. And just as Esteban was asking earlier, you could do the same thing in the y direction. And so, all right, there we go. And, oh, I guess I forgot to have you guess where it was supposed to be. But notice this one, it's basically approximately one grid line to the left and almost one full grid line down. So that's what we get in these numbers. Let's look at it and get a feeling for this. I know this problem is really easy, but it's worth it to get a feeling and get some intuition here. So it's somewhere over here. One full unit to the left, not quite one full unit down. That's where the center of mass of this is. So does this make sense? It seems pretty reasonable, right? If you look at it, 5 units of mass are way down here. Only 1 unit of mass is way up there. So it makes sense that the center mass should be below the origin. Similarly, you've got 4 units of mass on this side and only 2 units of mass over here. It makes sense that we're over to the left. And so, yeah, that's just kind of getting a feel for it and checking it. So again, if this is the center of mass, this seems totally plausible. The minus signs make sense. The units make sense. It's between all the objects. It's closest to the largest object. This seems pretty plausible to me. Any questions about that while we've got it up there? All right. And interrupt me at any time if I cut you off. Let's get to this here. Okay. If you're curious how a mobile works, you could do this problem, right? This is pretty fun. Look at this. I made a mobile out of bowling balls. This is great for hanging above a child's crib. Ugh. Okay, so basically don't make mobiles. That was a joke. Don't make mobiles out of bowling balls. But yeah, that's what I had laying around. We're going to come back to the calculus in a minute. Okay, we'll come back to that in a minute. Look at 9.31. All right. So in this case, how would you guys attack this problem? I'll give you a second to look at it. Remember, you've got the strategy on page 43. How would you attack this one? Anybody?
I guess it's split it into 3 different shapes.
Aha. So I like 3 shapes. Some people say 2 shapes. Either way would work. For me, it makes sense to split it into 3 shapes. And I'm assuming, let me just see if this is what you did. This kind of shape up here, this red rectangle, and then you did this separate rectangle below. Is that what you did, Dom?
Yeah.
Yeah, I agree. Now, again, we could have made one really big rectangle, but it's just easier for me because I know, okay, this center mass is going to be at, well, I guess this distance right here is going to be C over 2. This distance here is going to be C over, whoops, wrong color. Right? It's a rectangular plate. Unless we're told it's non-uniform, we're going to assume it's a uniform density, meaning it's the same amount of mass in every little chunk. I should be careful. That's negative C over 2 because it's to the left of the coordinate system. Whereas over here, this height is now negative B over 2, and that's really easy to think about. Whoops, not B over 3. And the height of this one, if I needed the y coordinate of the center mass, would be positive A over 2. Now, what about that triangle? Where's the center mass of that triangular piece?
1/3 from the fat end.
Yeah, so in this case, the x coordinate would be pretty easy. That's just going to be D over 3, positive. How about the y coordinate?
A minus A over 3.
Which is
A, so it's 1 minus 1/3, so 2/3.
2/3 A. So I see all the different x and y coordinates of the center mass. From here, all you have to do is plug into, give me a sec. We're going to use this equation. X center mass is equal to, oh boy. Sorry, I'm running out of room with all these Zoom things here. Sorry, that's a little bit diagonal there. I'm just running out of room. Okay, so then we could say, oh my gosh, x1, m1, and there'd be a mass 1 on the bottom. I could then go to x2, m2, just like I was showing you earlier. There'd be an m2 on the bottom. And finally, there's what, that dark green? So there'd be an x3, m3 with an m3 on the bottom. You should always have total mass on the bottom. And the idea is you could repeat this in the y direction as well. And you get a bunch of letters with fractions and plus and minus signs in there. And you just shove all that junk into here. Now, wait a minute. How do we get the mass?
I guess if we had density, we could figure out mass by volume.
That's okay, but we don't have the density. However, let's take what Esteban was saying a little bit and explore it. Let's just start with M3 because I have my green marker here. So Esteban's saying mass 3 is equal to density of 3 times the volume of 3. That's what you're saying. Agreed? That's good. Now, it turns out we're going to assume it's a 2D plate. And this is something we haven't discussed before. So we're going to actually write this as mass 3 is equal to lowercase sigma times area 3. Now, sigma is something that has units of kilograms per what? What do the units of sigma have to be in order to make this equation work out?
Centimeter square or?
Yeah, or meters squared, centimeters squared, something like that, right? Because area, that's going to be in units of meters squared or centimeters squared, something like that. And so notice this mass needs to be in kilograms or grams or whatever. So obviously you could use grams per centimeter cubed or whatever, grams per centimeter squared, but we're going to use kilograms and meters for right now. So in this case, rather than writing things this way, for 2D objects, we're going to introduce a new density. I will go more into detail on that when we get to calculus problems. So I promise I will come back to explain this more. But for now, think of sigma as mass per unit area. Okay. Now, when I see this, it says this thing has uniform density. So that means sigma 3 is going to equal sigma 2 is going to equal sigma 1. They all have the same density. And so I'm just going to call that density sigma. So they all have the same density. That's what this statement means. Uniform density. Every piece of the object has the same density. Now, I don't know if I'm losing you here, but I just want to point out this term right here should have a density in it. This term should have a density in it. This term should have a density in it. So every term in the numerator has density in it. Wait a minute. So does this one, and this one. Every term in the denominator will also have density in it. lo and behold, if we take this step of plugging in density, which we don't know, it will actually drop out and it will get all the masses in terms of areas, which we do know. And so we put in a constant that we don't know, it drops out, and the problem is solvable. Isn't that fun? Or torture? One of the two. All right, so I'm going to pause for a second while I find my mouse. Where the heck did it go? There it is. Questions on that? Did that make any sense at all?
So basically what you're saying is we can just plug in area for mass.
Essentially, we can plug in area for mass because you have to, yeah. So let's go look at the answer. You're right. We could, because the mass is equivalent in some way to the area times some constant, we could do this. So let me get back into, I hit the wrong button. This one here. Whoops. All right, so let's get into there. What problem was that? I forget what that was. I think it's the next one.
9.31.
Okay. There we go. So here's what I did is notice I put in a term density because it's a 2D object. I used a 2D density or sigma instead of rho. And so when you plug all that stuff in, you get this ugly equation. All of the terms have a sigma in it, like we were saying. So I'll leave this up here just so you could see it all. Sorry if that figure's a little hard to read there. I should have, I don't know. Maybe I could have done it a little smarter, but all right. And then it's just doing some algebra and cleaning up some fractions, right? So notice the first thing I would do is get rid of that 2, right? So just multiply everything in the numerator and denominator by 2, because that's the most common fraction. So that'll get rid of this, this, this. This is going to be, and it would be a 2, and it would get rid of this. And I think that's right. So each term, except for these bottom ones, has a half in it. So now, yeah, and then at that point, it's just rearrange and try to make it look pretty, but it's just ugly. And that's fine. Let's scroll down and see if there's any questions about that. All right, so this right here, that's the answer that we get. All right. So let's go take a look at the next part of this question. All right. If we assume this figure is drawn to scale, should the X center mass be positive or negative? What do you think?
Well, definitely be negative on the X direction.
Yeah, it looks negative on the X and probably positive on the Y. Agreed? And so I know this seems silly. I'm just putting this in here to remind you that that's something you should check every time. Does your answer make sense? Do you have the right units? Do you have the right plus minus sign? Well, when we look at this equation, it's not obvious. However, if we look, it looks like D is a smaller number than C. This is C squared. This is D squared. And this is times A over 3. This is times A plus B. It certainly looks like the negative term will be a lot bigger, and we should get a negative center of mass. Everything in the basement is positive. So yeah, a negative over a positive would give me a negative value for X center of mass. So that's how you could check the plus minus sign with this algebraic expression. All right. Now, suppose some architect wants the same type of shape, but she wants X center mass to be above the origin. Okay, so maybe she's building a structure that needs to be supported and cantilevered over this one spot. Great. And she wants you to adjust the parameter D. So in theory, this is how you could use such an equation. You could plug in different values for D until the X center of mass is equal to what?
0.
Yeah. And so this is a practical thing we sometimes do is we want to set the center of mass to 0. And so then you could adjust the size of the object to make sure the center of mass fits correctly. So, all right, there's kind of a practical application of this for, say, an architect or a civil engineer. And then this was kind of fun, and I found the answer, and it surprised me that it was this weird answer here. So yeah, I'll let you kind of look through that and try that on your own. Okay, and now there's one more type of problem I wanted to look at before we go on. Any questions on this problem here? It's showing you how you could do center mass using this density substitution and a bunch of letters instead of numbers. Any questions on that or anything on center mass so far? Okay. As promised, let's talk about a problem with a hole in it, and then we're ready to go back and start the calculus part. Okay, so if we consider, this is a circular plate with a square hole cut out of it. All right. This shocked me when I did it. I did the math, and we're going to do it in just a minute. Before we do the math, let's look at this. Let me blow this up so it's bigger and I can draw better. Where do you think the center of mass will be? You've got a circular plate and you cut a square hole out of it. Where should the center of mass be? Maybe somebody other than Esteban or Dom. Take a guess. It's okay to be wildly wrong. I got surprised by this one too. If it makes it easier, what quadrant do you think the center of mass is located in after you cut the hole?
The third quadrant?
1, 2, 3. Yes. And then what I thought it would be like way over here, right? It turns out it's actually pretty close to the center, even with this huge hole cut out of it. All right. So yeah, good. All right. So we have some intuition. We expect the center of mass should end up being negative in the X direction and negative in the Y direction. Now, this is one of these problems. A lot of students think, oh, shouldn't I do some calculus on this part and do an integral here and do an integral here? And then, it's like, oh my gosh, please no. Right? If you want to do this one, this is probably better for the whiteboard. Okay. This is very similar to what we did before. Again, coordinate system. You got to have a coordinate system. Now, we're going to take a solid circular plate and cut a square hole out of it. So one of the things I want you to get used to is to avoid calculus. It's easiest if we think of this as being a solid circular plate minus a solid square plate. And so that's the style we have to get used to. So we're going to take the solid circle without any hole in it and subtract off. Sorry, this kind of looks like a dash. That's supposed to be a minus sign here. And we're going to subtract off this solid square. So another way of saying this is I'm going to let M1 equal negative. Oh, I should be careful here. We could say this is sigma area 1. Actually, I think I'm going to call this 2. That's the second one. All right. And this would be mass 1 is equal to sigma area 1. And the idea is instead of adding mass in the center of mass equation, I'm going to subtract it. Specifically, the center of mass equation is now going to read something over something with minus signs in it. not plus signs. So this is going to be x1, m1, and this is, oh, sorry, I did it again, x2, m2, and this is just going to be m2. So I've manually put in the minus signs. Okay, you could even say it's a negative mass or whatever you want, but I think this makes plenty of sense. Here I'm going to have x1, m1 positive, and m1 positive. So the idea here is we take this solid shape with a hole and split it into two solid shapes and use a subtraction in the center of mass equation. I'm going to pause there. And is everybody okay with what I did right here? Again, we're using this trick. We've got a plate, and instead we don't know the density, but I know the density when I plug it in is going to drop out. So the idea here is we rewrite masses in terms of the unknown density, knowing that the density will later drop out. Let's keep rolling here. I'm going to lower this down just a bit. So now x1, m1, that's going to be x1 times sigma. What's a good way to write the area of this shape?
2 pi r squared.
Careful, 2 pi r is all the way around. Pi r squared is the... Right? Okay. And then before I forget, let me do that on the bottom too. So remember, we need a mass 1 there. Okay. Next. Maybe we're using a minus sign. I know I need x2. What's a good name for this area? Somebody else. What do we usually use? What formula do we usually use for the area of a square?
Side squared.
Side squared. Now we are maybe you were hesitant to respond earlier because you're like, wait, this is R's and this is S. We'll do that in a minute. Okay. So, oh wait, I forgot a sigma, didn't I? Sigma times area. And let's just write it all in the same order. So you're seeing the sigma in the same place. And then down here, there we've got it. We see, even though I don't know the density here, it drops out. This would be the same as if you had a piece of cardboard or a piece of steel or a piece of chocolate, right? The center of mass would be located. Actually, the center mass, if it was chocolate, would be inside my stomach. So there is a small difference there. Now, how can we figure out let me show you the problem statement again, just to show you what was given. So far, nothing is that crazy here. But when I go over here, notice the only parameter given is the letter R. We're supposed to figure this out. I was not told the size of the hole. But we do see it sitting there. So as the problem is written, it's not acceptable to have S in the answer because S is not a given parameter in the problem statement. Help me. What can I do?
I was thinking maybe you could take this square and split it into 2 right triangles.
Okay, okay.
And the hypotenuse would be the radius R.
That's absolutely right. Trick. So we know the radius is R, and I know this side is S. This is a right triangle. So give me a relationship between S and R. This is a square plate, so what type of triangle is this?
So you have R cosine and then R sine.
You could do that. That's bad. Because then cosine and sine of what? Because you need an angle. What angle would it be?
Well, wouldn't it be 45 degrees?
There you go. So then you could say cosine of 45, but usually we just say, isn't the hypotenuse of a 45, 45, 90? Don't we know that R equals S times root 2 from a memorized geometry formula? Which is kind of where you were going, right? So, or let me check this another way. We could say something like this. We could do S squared plus S squared equals R squared. So maybe if I do that down here, I know that S squared plus S squared equals R squared. So notice 2S squared equals R squared, or root 2S equals R, or S is equal to R over root 2. Now, Esteban, you would have gotten a similar result there because cosine 45 is 2 over root 2, or sorry, root 2 over 2, which is the same thing as 1 over root 2. So you could have gotten there using trig. I do think for the last half of the semester, it's good to remind ourselves of the Pythagorean theorem and some basic geometry tricks. They're really important in chapter 12. So what you said was a good idea, Esteban. This is also a good idea, and I think it's important that you know both. That's why I'm stressing that. Is everybody okay that we can get this relationship now? That's what we need to focus on right now in one of these ways. I'm going to hope that's good. The idea is plug that crap in. Ooh, wait a minute. We're not quite done yet. We've figured out what S is going to be. And in fact, I think I have it right here. S squared is going to be R squared over 2. So from all of this junk, you're going to find out that this is R squared over 2. Notice the R's drop out. What are the X's? What is X1 for this problem?
0.
0. So this term drops out entirely. X1 is 0. What is X2? In terms of S, what is X2?
So it'd be S root of 2 divided by 2.
Nope. It's just S over 2. Which is, I think, what you said, it relates to R that way with those 2's and root 2's. But do you agree it's just halfway over? It's a square. Halfway over is the center mass for a square, which is S over 2. S is then R over root 2. And maybe, is that what you meant to say, Esteban? I don't know if that's what you meant.
No, but I saw where I was confused.
Okay. But does that make sense now?
Yes.
Okay. Yeah. And so this is pretty sloppy. Why don't we look at the solution and kind of go through it just to make sure everybody's got it? Okay. So you could, this is kind of helping out. So notice the diagonal of the square is root 2 times the side. That's the trick I used. But like we said, there's many correct ways to get that. What am I doing? I'm writing down the masses in terms of the densities. I'm writing down the positions, and then I shove it into this formula, do the math. Notice we should check the units. It's only shifted by 7%, less than 7%. Isn't that crazy? I thought it would be much, much shifted by much more. So in the end, if we looked at this one, that's what, 1/7 is about a 14th. So if you divide this into 14 parts, it's like right there. or maybe even closer. It might be even closer to the center there, but approximately right there. Cutting that huge hole out of this circle does not shift the center of mass that much. Now, I don't know, maybe some of you might be saying, this is dumb, this is pointless, who cares about this? Let me give you another example, very similar to this one, and see if you could maybe understand why this might have some meaning to some people. Imagine you take a circle and you cut a circular hole out of it. You could imagine this is a cam, right? And so, right, you could imagine you have a cylindrical shaft here, and you're going to mount these onto here. Sorry, my picture's bad. But the idea is you could use these to open valves on a car engine or something, right? So maybe this is one, and then you're saying, well, shoot, how far off axis is the center of mass, or what do I have to worry? What if I put multiple of these on here so that there's another one here? All right, whatever. But so, all right. You could imagine this might relate to cabs, camshafts, things like that. That's enough on that. I don't know. Let me get this back up here and see. Any questions on this first part of the strategy now? Let's go look at it and see if there's any. I'm trying to give you some ideas for this first part of the strategy without calculus. Let me zoom out. Get back up to that. So we have talked about how to handle these types of problems up here, these first 3 bullets of the center mass strategy. Any questions about those 3? All right, so let's go ahead and take a break, and then we'll come back and we'll attack the calculus. So let's just say 107. Let's be ready to go. 107. All right, and I'll just leave the live stream running. We'll do this here. All right. Oh my goodness. Here we go. Any questions before we start back up? Just getting some water here. By the way, I'm not a Houston Rockets fan. I just got a free cup. That's all. All right. Let's see. Where were we at? Okay. So center mass. We're going to finish this today. Now we need to talk about calculus. So the shortest way I can say it is I want you to completely understand everything on the bottom half of this page. If I zoom out a little bit, basically you need to really understand all of this stuff. That's quite a bit. Let's make it even smaller so we can get it all in one shot. There. So this is the calculus portion. You could see it's its own beast. Now, what are we going to do when we do this one? Imagine you have some object here. Let me just give a reference object. Let's say there's some object and it's not easily split up into chunks. Now, you could argue you could approximate this by a rectangle and a triangle, and I'd say you're right, and that might be good enough for a lot of engineering applications. But let's say you really needed to know where this is done exactly. The first thing you would do is actually, as a practicing engineer, you'd probably figure out how to draw this shape in CAD and hit the center of mass button. But let's kind of understand what's going on under the hood in such a program. One of the things we always want to do is have a coordinate system. So you've got your coordinate system. Otherwise, you can't define functions to do calculus. Now, if we want to figure out an x coordinate of a center of mass, I'm going to read this. We need a dx. Okay, so if you want to get x center of mass, you need a dx. Should my slice be horizontal or vertical if I want to get the horizontal coordinate? What do you think? I'm going to slice this object up. Would I want to do a horizontal slice like this?
So vertical slice.
Yeah, we would want to do a vertical slice because that would give us a small term here, dx. Got it? So that's what I'm trying to say with bullet points A and B. So if you slice it vertically, you're going to get the horizontal center of mass. Okay, we see the first place people might screw up. Now, use the appropriate density equation to relate mass to one of these things. That's what this table is down here. If you have a 1D object, for example, a thin rod or a wire or a thin rod that's bent into an arc, those objects can be considered as one-dimensional objects. They are going to have linear mass density. Notice that's mass per unit length, or kilograms per meter. If you have a 2D object, we're going to use this term sigma, which has units of kilograms per meter squared. We were using that already. But notice that's going to be, if it's uniform, that's total mass over total area. And then this is the standard 3D volume mass density. So this is the normal one that we used to use all the time. It turns out that's a waste of time in many situations. So it makes problems harder to do 3D if you don't need to do 3D. So to be clear, if you have thin rods, wires, things like that, we're going to call this a 1D object. If you have thin plates, triangular, circular, rectangular, stuff like that, we're going to use a 2D density, kilograms per meter squared. And then for solids like spheres or frustums of cones and things like that, we might use this 3D density that we've always used before. Now, so let's look at this example up here. This is a 2D object, right? This is a 2D object. If you have a 2D object, you're going to need a 2D slice. Now, some of you might say, can't I just do this with 3D calculus? You can. And we'll do it that way in lab in a bit. But for now, the only math that we can use is Calc 1. Actually, I think Calc 1 and Calc 2. So we could do 1D integrals right now because that's the prereq for this course. So are there other ways? Sure. But this way works great. So let's just use it. If you have a 2D object, you get a 2D slice. It looks like this. The width is dx. The height is y. So the area of that slice, dA, is equal to y times dx, right? That's the area of this little slice of that thing. You might say, wait, is this a rectangle? Is it a trapezoid? Well, if it looks too trapezoidal, cut it skinnier, make dx smaller until it looks pretty much just like a rectangle, all right? Now, in this case, I could plug in this dA right here, plug that in, and notice I would get units of mass. Kilograms per meter squared times meter squared equals kilograms. So you're probably not used to looking at units when you do calculus. When you do physics problems, you can use a unit check to verify you have the correct integrand inside of your integral before you waste time trying to integrate. Use that unit check to make sure your integral will work out. It won't always get you bomb-proof results, but it will help you find some common mistakes. All right, so now in this case, y would turn out to be some ugly function, and we'd have to figure that out. But so far, we have done how to slice it and how to write the dm. This is the integral we want to use. So I have now figured out this piece of the integral, and then the hard part is, what are the limits and what is mass? Well, if you need the mass, you could do this integral. So, well, we already know dm. Again, we got to figure out the limits. So there's going to be some effort put into figuring out the limits. But most of the effort in these center of mass problems is figuring out what the heck is dm. All right. Now, one last bit of knowledge here. I know I'm skipping around a little bit. Look at this part D. If there is no comment made in the problem about it being non-uniform, we are going to assume it's uniform. Again, uniform density simply means you have the same density at every single point in the object. That is not always true. If it's not true, I'm going to give you an equation and you could plug it in. All right. So essentially, if the problem has a uniform density, you need to figure out the density using one of these three equations, depending on which shape your object is. If it's non-uniform, I'm going to give you this equation and you don't have to figure it out. Okay, that's a lot of junk on this screen. Does anybody have questions right now? I think we should just do some problems and figure stuff out.
So dm varies depending on whether it's 1D, 2D, or 3D, right?
Yes. So looking at this, the dm is the hard part. If you're using a 1D slice in the x direction, right, it's going to be lambda dx. If it's in the vertical, it's lambda dy. If it's for an arc, you get this weird combo, right? An arc might look like this. Is that helping for 1D?
Mm-hmm.
And then if it's 2D, you're going to do some geometry to figure out dA. Is it x dy or is it y dx? And then how does y or x relate to the other variable? What's an equation for the function that relates y and x? And then similarly down here, rho dv.
Why is it that
Go ahead.
that integral you showed, the function or the formula for the integral, why does it look so similar to average value theorem?
Because that's what center of mass is. You're getting a weighted average of the mass positions.
Huh.
So this is right. Let's think about it. Let's say we take a big mass and put it right here and a small mass and put it right here. What does the center of mass equation do? It's a weighted average. It's just like a grade calculator, right? Like what if one part of your grade weighs more than the other? Well, then getting a negative score on that would really stink. So again, it's a weighted average of the positions of two objects. And so similarly, if we take this one that I was drawing right here, it's funny because in the lab, I actually have shapes cut out like all these, and I didn't think to grab them over spring break. My bad. But yeah, so I actually have a bunch of objects cut into all the shapes of these problems to hold up and show you, and I forgot to grab them. Dumb, whatever. But yeah, so in this case, what you're doing is you're splitting this into slices. So let's say this is slice 1, slice 2, slice 3, slice 4 is a little bit bigger, slice 5 is a lot bigger. And what you're doing is you're doing that weighted average of each of those slices. Remember that an integral is very similar to a sum, right? So what we're doing when we do these, this is sigma notation now. You're saying sum up the weight of each mass. The mass, you can think of the mass as being the weights, right? So this position times its weight. And then you add up all the weights and you better get 100%. Is that helping, Esteban?
Yes.
It's exactly the same as a weighted average.
Okay.
Now, another reason I go so crazy on this stuff, the mathematics that you see here shows up again in physics 163 with vectors in the integral as we talk about charges and magnetism and currents and all these different things. So I go pretty serious on this integral calculation of center mass because we're going to use similar math later on. By the way, maybe now you understand why I do all those strange problems in chapter 1 where there were holes cut out, right? All these things start to add up and we're starting to see more and more of the pieces of chapter 1. So, all right, whatever. Let's do this one. Yeah, so let's take a look. We've got a uniform right triangular wedge. Obviously, we know the answer to this. I already told you, but let's use calculus on this simple problem to see how things get set up, okay? So we're going to slice this thing. I sliced it in this way. Oh, look at the coordinate axes carefully. Let me make this a little bigger. Back it off just a little bit. There we go. So we're looking at 9.29, which is on page 45. Those of you that did this problem in math class, it's a little different. Just trust me. There's a reason to do this. Okay. I'm going to get this drawn up and then we can talk. If you want, you could race ahead following the solutions or whatever. 9.29. So we're told this height is h. This is L. That's W. And all right. So when you see this, and there's that slice drawn for you, this slice that's shown right there, which coordinate of the center mass are we going to be figuring out in this picture? Is it going to be X coordinate of center mass, Y coordinate of center mass, or Z coordinate center mass?
Probably the Z coordinate.
Nope.
Y coordinate.
It's going to be the Y. And let me show you. So this part is a little bit weird at first, and that's why I was asking. So it's okay that you screwed that up because we haven't done one yet. It's sneaky. Take a look. Sorry if I can. Oh, marker, come on. This is my attempt to draw that slice. Sorry, it's not perfect. But the idea here is this distance here is Y. This little distance, the thickness of the slice, is dy. And that's how I know if you have a dy in your equation, the dy is going to give you a Y coordinate of center mass. I don't know who asked that, but hopefully that makes sense why. We switched the axes. We made a vertical slice. There's a tiny amount in the Y direction. So the thickness of our slice is tiny in the Y direction. That means I'm going to have a dy appear somewhere. That implies I'm going to get a Y center of mass. Okay, so that's part A. I'm going to read the question and see what's next. Oh, this is a 1D, 2D, or 3D object, 3D. So should I be using lambda, which has units of kilograms per meter? Should I use sigma, which has units of kilograms per meter squared? Or should I use rho, which has units of kilograms per meter cubed? Well, we have a 3D object. That means I'm going to need a 3D slice. That means I need to use this one. So the idea is the density of your slice should mirror the dimensionality of your slice. So if we have a 3D object, we have a 3D slice, we'd better use a 3D density. So in this problem, did it say anything about it being uniform or non-uniform? Uniform, right there. Uniform means you figure out the density. So 3D uniform density, that says rho is equal to mass total over volume total. In this case, the mass, I'll just call capital M. What was the volume of this shape?
LWH.
That would be if it was a rectangular solid. It's triangular.
Oh, 1/2 LWH.
Yeah, so it's area of the base times the thickness. Well, 1/2 HL would be the area of this face, and then times the thickness. So 1/2 HLW. So notice, I'm just going to flip this 2 to the numerator, multiply top and bottom by 2. So the density in this particular problem is 2m over HLW. Now, in a lot of problems, it doesn't matter if you made that screw up, because in a lot of problems, as we've seen already, the density drops out. However, let's get it right just in case. All right. Let's get back in there. So we got the density. Determine the height of the slice Z. This is, okay. Any guesses? I want the height of my slice Z in terms of the distance Y, or that position Y, I should say. Any guesses?
I'm sorry, can you repeat the question? I didn't hear it.
I want the height z as a function of y. Now, a lot of you in your calc classes say, can't I just use similar triangles? That doesn't work on this one, right? These calc teachers always teach you the easiest possible methods instead of the most general possible methods. It drives me crazy, right? How could you get the height of this particular slice? Let me ask you this. Is the height of the slice going to be a parabolic function, an exponential function, a sine function? What do you think?
What's a linear function?
A linear function. So what is the general function of a line? Well, how about we write it over here? Most of you know it as y equals mx plus b, right? This is not going to work out well for us because m has a special meaning for us. M means mass. So, and in this case, y is the horizontal coordinate. And so this is bad. We need to modify the standard equation of a line to fit our specific problem. And this is what math teachers are terrible at, right? They don't force you to think through reality. In this case, z is the upwards direction. That's what k hat means. Y is now like the x direction. So what? If I want to modify this, z should equal, write out the word slope. Don't mess with yourself. Just write out the word slope. Slope times y plus intercept. And if you get used to doing this for physics problems, writing out the word slope and intercept, you might save yourself some mistakes and a few headaches on, a few handful of problems over your career. Now, what is the slope?
That would be the hypotenuse of the triangle, right?
Okay. I need an equation for the slope. In general, how would you like? I'm trying
So
not
would
to give it
that
away.
be the square root of h squared plus l squared?
That would be the length of the slope, but that is not the slope.
It'll be y squared plus z squared.
No. You guys are making this too hard.
H over L.
Why?
Rise over run. Isn't that always slope? What is the rise? Well, let me just write this out. What's the intercept here?
H.
H. So H is, so what is the rise over run for this problem?
So h over L.
Nope. It's not H over L. I think that's what you said too, right, Nick?
No, that was someone else. I said Z over Y. Someone else said H over L.
Oh, okay. So it's similar to H over L, but that's not right. I like that positive attitude, but that doesn't work for this slope. That's
Damn negatives.
Negative H over L. Agreed? It's H over L in magnitude, but it's going downwards. The rise is negative H. The run is positive L. So that's what you get here. And now, okay, whew. This tells us the height in terms of y. You tell me a number for y and the numbers for L and H, and couldn't I tell you a value of the height of the slice, z? So notice this is the height of the slice, z. All righty. What do you think about that? Any questions? using the meaning of y equals mx plus b is not obvious because students haven't been pushed that hard. You need to know what this means and how to apply it to a random scenario. And once you do this a couple of times, you're like, oh, okay, that's all it is. And then you get really good at it really quickly. But this is huge for engineers. Why? So many things we approximate with lines. And so it could be tension as a function of distance from the pivot point or whatever. There's going to be a large number of things that you need to write your own line equation, and it's not always going to match up to y equals mx plus b. You got to adapt it a little bit to your own problem. All right, let's get back over here and see here. Oops. All right, so what's next? We did parts A, B, and C. Determine the mass of the slice. Okay, so now let's go over to here. We just found that Z is equal to negative H over L times Y, whoops, plus H. That's what we just found. We know the density. I know the value of Z. This part is Z. What is dm? The mass of one slice. What is dm? In general, we're dealing with a 3D object. dm should be 3D density times a small amount of volume. Let's think about this. I have a small amount of mass. Density is a macroscopic quantity. It's a big number. So in order to get a small amount of mass, I need to multiply by density by a small amount of volume. Okay, this seems reasonable. So dV is a sign that it shouldn't be length times width times height, or even 1/2 of that. I need the area of this tiny slice. Oh, sorry, the volume of this tiny slice. I think I said area there. Apologies. Well, this side is height Z. What's this side right up here? Sorry, let me use this. What's this width?
W.
W. And then what's the thickness here?
dy.
dy. So this is density times Z times W times dy. Now, sorry, there's a little glare there. In this case, I know a function for the density. I could plop that in here. Boom. I know how Z relates to Y. So I could write Z in terms of Y. So I have a Y thing in here to do a Y integral, and the math will work out. This is not easy. You need to know all of this. I don't know. Is that making any sense? Any questions right now?
And the integral will be from 0 to L?
In this case, let's write the integral before we figure out the limits. So I'm just going to keep working down the page, but I'm going to do this. So we'll keep this up here. We can come back to it. So now here is the center of mass integral in general. I'm going to sit down because this board's so low. If I want to get the y coordinate of the center of mass, that will equal the integral of y times dm over mass. But if you don't know what the mass is, you could always figure it out as the integral of dm. Now, in this particular problem, we were already told the mass is just capital M. But I want to point out, if you stuck this junk into here, you could integrate it, and it should turn out to be the letter M. So for this particular problem, I'm going to make it a little bit simpler and just write 1 over the total mass times the integral of y dm. Now, if I plug in what dm is, give me a second. That's rho times z times w times dy. And now Esteban's saying, wait a minute, isn't the limits from 0 to L? Well, let's think. 0 is the smallest value y could be. L is the largest. So yes, Esteban, you are correct. That's why the limits go from 0 to L in this particular problem. So far, so good?
Yeah.
Right on, right on. And again, what we could do is, well, let's take a look. Before we do anything, what is a constant and what will pull out of the integral? Is y changing in this problem? Well, yeah, I'm changing y. That's the whole integral we're doing. We're doing a y integral. How about rho? Is rho a constant or is it not constant?
Constant.
It's constant, so that can pop out. How about z? Is that a constant with respect to y?
Z depends on y, right?
Z does. And so that we can't pull out z. How about w, the width?
Constant.
That was a constant. We could pull that out. And so this integral actually comes a little bit easier. We could worry about these later by saying, well, this is rho times w. All right. And so it's getting a little bit less ugly now. We stick in this big mess and do the integral. We're good to go. Let me ask you something before we do that. You could do this same problem if it was non-uniform. I deliberately explained it in a way so that we could do this problem if it was non-uniform. Check this out. Imagine that one word in the problem didn't say uniform. The only difference is this is not valid anymore. Instead of using this, you would use some equation I gave you. And instead of the density pulling out, you couldn't pull it out. And instead of knowing the mass, you'd have to do an integral where you say m is equal to the integral of dm. And then you'd plug this in. You couldn't pull out, but you could do this. It's the same problem if it's uniform or non-uniform now. So that's why I tried to explain it this way. And I may not have, I don't know. I hope that makes sense why. Let's go look at the solution and see what else I forgot. Okay. So this is 9.39. Oh, 29. Excuse me. And I know I'm going a little bit slow here, but I'd rather go slow on the first one. And so I'm trying to show you this in a very general way. I know the answer is 1/3, right? Why are we doing this pain? Take a look. You can walk through this now. Okay. The surface of the slice head thickness dy. That's what clued us in. If you see a dy in here, you know you're going to get the y coordinate of the center of mass. Now, if it's a uniform 3D object, that's what allows us to use this formula. Uniform 3D, use this. Non-uniform, don't use that. Watch out for that factor of 1/2. Next, the height varies linearly. The equation of a line in the YZ plane is this. Instead of y equals mx plus b, it's z equals slope y plus intercept. The slope is rise over run, so it's negative h over L. The intercept is h. We get this equation. Ooh, notice I factored out the h over L here. That's useful because this part will pull out of the integral later, right? All right. Oh, here's something I forgot to mention. Anytime you write your own equation of a line, double check. If we plug in 0, the L's drop and we get H. If we plug in capital L, we get 0. So notice if you check 2 points of your line and they both work, your line equation works. So that's a good idea to do that. So check your equation. I forgot to do that. Okay, in case you're wondering why I rewrote it. Okay, let's see. 3D object makes a 3D slice. Mass of a 3D slice is this from the table. Then we plug in all that junk, plug in all that. It gets this ugly crap. Notice a lot of this stuff out front, all this is a constant. Okay. Now, the center of mass integral. Here we go. And notice I said here, why not check the units before you do the integral? Let's check the units. What are the units out front? We got 1 over meters squared. What are the units inside the integral?
Meters squared.
Meters cubed. dy is a length. This is meters squared. dy has units of meters. dy means a tiny bit of length. So dy might be 0.0000001 meters, but it's still in units of meters. Does that make sense? Was that Dom?
Alan, yeah.
Alan. Sorry about that, Alan.
No
Alan,
worries.
does that make sense?
Yeah, that makes sense.
Okay, so watch out. dy has units of meters. You can see when I write it in here, that's because everybody forgets that. So that's why I'm saying it. So it's good that you spoke up. Now, wait a minute. We get meters squared. We get meters. That makes sense. Why center of mass position should be in units of meters. So that's why I'm checking that to make sure I didn't screw up a squared or something. All right. All right. In this case, the smallest value of y is 0 to the biggest. It's just L. You get this. All that work for 1/3. Isn't that crazy? It works out to be 1/3 from the fat end. And so you would never do this problem using calculus in the real world, but it's a good example. Whew. All right. Notice the width dropped out and the height dropped out. It's valid for 2D or 3D right triangles. You might want to emphasize this is valid for a right triangle. Ooh, let's go back and see the next question. Okay. Take a guess. How much mass is to the left and to the right of the center of mass? What's your gut tell you? Let's remind ourselves what this looks like. We've got a triangle here. I'm going to do a pure side view so it's easier for me to draw. Eyeballing it, that's about halfway, so that's about 1/3. Let's say we cut this thing in half like this. Okay. How much mass is on each side of that line? What do you think? Does one side have more mass than the other, or do they have the same? What's your gut tell you?
Would it be the same?
And what's kind of the intuition that's driving you there?
Well, it says it's a center of mass, so.
Yeah, so you'd think you'd be right. Take a guess what I'm going to say next.
I'm wrong.
Yeah, isn't that weird?
Yeah.
So look at this. I mean, come on. It says center. It's not true. Even here, the volume to the right is 2/9 this. Well, the volume, and so it turns out there's more mass on the left side than on the right. Isn't that crazy? One thing you can think of, if this helps you, this mass, right? If I just imagine this piece, the center of mass of this piece is probably right about here. The center of mass of this piece maybe is right over here, a little bit farther away. I know that's not obvious, but let's say this distance is D, and this distance here is Q. Q looks a little bit bigger than D, ever so slightly, right? And so as a result, if you want to balance this thing, the center of mass of this piece is less far from the axis of rotation. You need more mass on the left side to balance the torques. And it turns out, oh my gosh, we're going to cover this in chapter 10. But center of mass is actually relating torques or moments. And so trying to understand more about this equation without chapter 10 is a challenge. Know this, the center of mass is not the spot that cuts the mass in two. Let me give you a simpler example. Let's say I put a 2-pound bowling ball here, or a 2-pound ball right here, and a 1-pound ball right here. The center of mass would be right about here. If I cut this, there's clearly twice as much mass on the left as there is on the right. Right? And so the center of mass is never, very rarely going to be a spot with equal mass on equal sides. Only for the simplest possible shapes. Like if you do a circle, yeah, there's the same mass on the left and right. But if you do a half circle, no. Not necessarily if you do the vertical coordinate of the center mass. Or if we do a triangle like we just saw, there's not the same mass on the left and right. All right, so try not to be fooled by that. Yeah. All right, okay, whatever. Let's go back. Whew. Okay, what is the XYZ coordinate of center of mass? Well, how would I do this in the real world? Let's say we just did calculus for this and we figured out that this one is at L/3, right? You could do similar calculus to show this is at H/3, or just know the answer is H/3. And then finally, look at the Z coordinate. We don't even need to do an integral. What's the Z coordinate of center of mass?
W/3.
Nope.
No.
W/2.
Nope. Oh, I guess I should say it's negative because this is indicating positive, right? Let's double check. I comes out of the page. Yeah, so it would be in the negative direction. Do you see that? That's what I was. All right, whatever. So this one is the Z coordinate. This one is the I coordinate. I think I misspoke too. So I got myself with my own tricks. All right, but whatever. So yeah. All right. There's all the different coordinates for this. You can just use the symmetry, and remember, always think about plus minus signs. All right. Okay, 9.30. Are we ready to try this one or not? You guys ready for it? Let's take a second, see if you can get it set up. I'm going to pause and let you get a look at it. I'll write my whiteboard up. Okay. Hope I'm not losing you with this. I really like this stuff. I think it's fun. And actually, while you do that, whoops, stop the share for a second while I get something else up. Okay, so you guys go ahead and look at that one. Let me bring it back up for you. Sorry. Let's put that back on screen. No, this one. Yeah, there you go. And then while you do that, I'm going to open up another. Whoops. Sorry about that. Okay, that's ready. 9.30. All right. Let's take a look at this. We've got y here. We've got r. What's this thin dimension of the slice? Is it going to be dx or dy here?
UI?
dy. So notice I'm constantly changing the coordinates just to keep you on your toes, and I hope that's not screwing you up, but it's important that we always think here about our coordinate systems, and that is going to be important when you go on to be an engineer. All right, so I know it seems like torture now, but I'm telling you, everybody you look on the web might use a different coordinate system, so you got to always check that. All right, so in this case, is this a 1D, 2D, or 3D object? What's your guess?
2D.
2D. What was the key word?
I just said in the problem.
Oh,
9.30
okay.
2D calculus.
Oh yeah, okay. Oh, that's true. That helps. The keyword plate also helps. So plate is what tells us 2D if we didn't have that 2D calculus. So, all right, so then which density am I going to use? We've got a 2D object. I need a 2D slice. So I need a 2D density, which is
Alpha.
nope,
Sigma.
sigma. So this is the one that's kilograms per meter squared. So we're going to use a sigma for here. Circle with a horizontal line on top. Okay, sigma. Now, all right, so what's dm going to be? Or well, actually, let's start this way. Let's go in order. Okay, so we've done parts A and B. Part C says, in terms of y and r, determine the area of the slice. So dA, the area of my slice is small. I want to use a dA. What's the area of this slice? In terms of y and r. How about this? What's a good name for this distance here?
You can call that H if you wanted to, I guess.
Okay, we could call that H. So it's going to be H times what?
Times dy.
H times dy. Now help me. We know that this distance right here is y. I know that this distance right here is r. Sorry, that y is really small. I know this whole thing is distance h. That's h. So this side right here is h over 2. Sorry, that's so small. That says h over 2 right there. How do I figure out h?
Can you do the square root of r squared minus y squared?
Pythagorean theorem, right? So I know that h over 2 squared plus y squared and then from that, couldn't I solve for h and shove it in? Now I have h in terms of y. R is a constant. We're good to go. I'm going to pause there. Does that make any sense? Or are there any questions? We use geometry to figure out this relationship. In the last problem, we use the equation of a line. In some other problem, you're going to use the equation of a parabola. In some other equation, we might use the equation of something else. So the idea is this step is always different. This step requires you to use anything from any branch of mathematics, geometry, graph theory, whatever. So, all right, All right. So this is a hard thing for students. They have to use their math creatively. That's what makes it fun. That's what makes it hard. Okay. You have to actually understand everything you were taught in your math classes. God forbid. All right. Now, let's go on from here. Now we've got dA. So what's the mass going to be? dm is sigma times dA. Well, I've got an equation for dA. In theory, I could get h from this junk and shove it in there and plug it in. What's sigma? What's sigma? How do you get sigma? Is this a 1D, 2D, or 3D?
It says total mass divided by total area.
Total mass over total area. In this case, let's just say the total mass is m. What's the total area?
Half of pi r squared.
Half of pi r squared. We've got all the pieces. What's my integral going to be? If I want the center of mass, the y coordinate of the center of mass will equal the integral over the integral of y dm over dm. What are the limits?
Negative r.
1 to 1.
Not negative 1 to 1, not negative r. What is changing in this picture? What coordinate is varying?
Oh, the y.
Y, what is the smallest value of y and what is the largest value of y?
Well, r and 0.
0 to r. So notice we see the hard parts of these problems are getting this frickin' equation here and figuring out the limits. They're easy to screw up. No one part is that hard, but these two stand out as the places that most people make mistakes. Also, if you grab the wrong density, you're going to make this problem harder than it needs to be. Okay. Let's go look in the solutions and see what else is there. Okay. And then I got a little treat for you. Cyber treat. All right. So we looked at this one. Oops. Here it is. So what I did is I just called that thing X, and then I called the whole width 2X. I think we called it H, and this distance, instead of calling it X, was H over 2. Same problem. Now, okay, we keep going. Notice I checked my answer before moving on. Both limits made sense. So my particular area was 2X times dy, which was 2 times this. So we should all have the same answer here, regardless of whether we use X or H. So here is dm. Now, we did the step of figuring out sigma. It turns out, look down here. I don't know if you could see this. Because this was a uniform density, I didn't even bother to figure it out because I knew the uniform density is going to drop out, right? If density is uniform, it drops out. If it's uniform, it will drop out. Okay, so in this case, that drops out. So does the 2. And then you get this weird result. On an exam, you could just use Wolfram Alpha or something. So make sure you know how to use it. But I did it with fun. You might be wondering what type of thing to do. If you see these types of things, that reminds me of this type of shape. That reminds me of trig. That's a sign that you might try a trig sub. So if you see a triangle popping out of your math, that's a sign you should do a trig sub. But so I did all that math for you, and I got all this junk, and there you go. Now, let's just take a look at this. Let's just run this. This is what you are doing. You're building up that shape out of all these slices, right? So the idea now in the coding, I had to do it in 3D. So it makes it a little bit trickier. But the idea is this is what the integral is doing. You're adding these slices one at a time. And then you can output the y coordinate of the center of mass. Now, when we go into here, maybe we should read this. I chose a radius of 4. So maybe we should change this radius to 1. And then notice I used a uniform sigma. And then let's see here. I used 21 slices. Now notice here, there's going to be, you're going to do this in lab later. But so notice you're writing this in code the same way you did the math, because you're just adding these up. We're going to learn what these symbols all mean later, but all right, whatever. I did some tricks here. All right, let's just run this again and see what we get. When the radius is 1, sorry, I got to zoom in. So in this case, notice that the center of mass I get from this code is about 0.41. If we look at the solution, I got 0.4224. So this is good. It's not perfect. So what I could do in my code is I could come into here and edit this and try using 42 slices, or how about just 51, right? When I run this, it's going to take longer to compile, but hopefully I get a smaller mistake. It's adding up all those slices in there, adding them up, adding them up. We see this starts to look more and more like a circle. There's a little aliasing there. Sorry about that. And as we go down to here, notice we're getting closer and closer. We're converging on the correct result. One of the things students have trouble with is they believe their codes blindly. What we can see here is that when you get non-trivial problems, sometimes your codes get very close to the correct answer, but not exactly right. So we sometimes need to assess that. Let me see if I can find you another fun one here. You could see we could do uniform and non-uniform rods. There's triangles, frustums. You could do hemispheres, things. You could do arcs. So we can learn about these codes later. But the idea is if we go through this, we've got 10 minutes. Let's just skim through a few of these and we'll call this good. We've done most of this yet. If you had a 1D problem, and I'll be honest with you, on exams, I usually focus on 1D. If I'm going to do calculus, I will usually do a 1D calculus or a 2D non-calculus problem. So that's not true to a number, but in general, that's the kinds of things I like to do. So if I'm going to stick on a nasty non-uniform problem, I usually keep it to 1D. So 9.33, 33 and a third. Look at these two problems here. Here, I tell you the density. So if I tell you the density, let's look at how this solution shapes up. 9.33, 9.33. All right. Okay. Look at this problem now. This is a one-dimensional problem where it's non-uniform. Okay. The density is, what was the density? Sorry, I got to look it up. Alpha x. We were told that the density function was equal to alpha times x. Alpha is fish swimming left, okay? Fish swimming left is alpha. This is a constant. We were told this was a constant in the problem. So the idea now is, well, think about this. This rod is getting more dense as you go to the right. As x becomes bigger, the density gets bigger. Okay, so I could check the units. That's important for later. I check the units. My mass is the integral of dm. Well, dm is just lambda dx. Well, lambda is just the function I gave you. So in this problem, non-uniform seems scarier at first, but it's actually easier because there's one thing you don't have to do. You don't have to figure out the density function. It's given to you. You plug that in, you get this weird result. Now I know the mass to stick down here in the basement. Well, here is x times dm, so it's x times this. So when you start doing these over and over again, you start to see these patterns and you get faster at it. Okay, so this is actually very similar to a triangle if you think about it. If the mass increases linearly, you're 2/3 from the fat end. or sorry, 1/3 from the fat end, 2/3 from the origin. So this would be like a triangle where the mass is increasing linearly. Oh, that's cool. Whatever. Let's go back to here. I know I'm going a little bit fast now. I'm just trying to squeeze in whatever I can. What if the density was this power? You could work this out. What if it's some arbitrary power like this, and you know where the center of mass is? So this is a good variation. These 9.33s, they're all really good variations for figuring out 1D. So make sure you do those carefully. 9.33s. If you're wondering how you could create such a thing, I actually made one in the lab this way. I took a piece of wood and I attached strips of aluminum to it, and it looks a lot like a staircase. And then rather than view this thing as 17 different pieces of metal and a piece of wood, what you could do is you could just say, look, I'll get the density of this portion. I'll get the density of this portion. And I did that. And then you say, assume the density varies linearly. I got the density at the left end. I got the density at the right end. And I know that the density as a function of x should be some linear function, slope times x plus intercept. And then what you do is you do trial and error to figure out what the density function is, just like we did earlier today. And so these were actual numbers from a real piece of wood with aluminum on it. And I found this as the center of mass. So if you're wondering why we would ever use a non-uniform density, this is one case. Or perhaps you've heard of things like p orbitals and in chemistry and things like this. In quantum mechanics, we were going to do some stuff that involves probability density functions. So this is in physics 162. So all of these regular density calculations relate to probability density. What about electric field calculations? The same types of things. So even though maybe this scares you a little bit and it's new, I'm telling you, learning to deal with these weird problems will help you out in later classes in physics, okay? Here's another one, and it says, rather than finish it, just show you get to this step. This is a cool one. Here's one where you have to use a parabola instead of a line. So I'll let you deal with that one on your own. Here's one where it puts it all together. This is a fun one. So you got a circle, a hole, and then a something with a fractional exponent. So this is a good one to practice there. But at this point, it's all the same junk. And notice 3D calculus, because it says challenge, that means it's not going to be on a homework quiz, but sometimes this will help you understand these things. Okay. Yeah. So if you want to do those or read through those solutions, this is a fun one. If you need an arc, I don't know if you remember, we mentioned arcs. So this one talks about the high jump. Maybe you have heard of the Fosbury flop in the high jump. It turns out by doing this, bending your back this way, your center of mass is actually below your body, and you end up, you launch yourself like a stream of water over the bar, and you can lift your body higher than you can lift your center of mass by arcing it. And as a result, you can increase your high jump and win the world record, and people think you're crazy until everybody does what you do. It's a really cool thing. I know we're running out of time here. Look at this weird one. I know this may seem silly, but I just want to point out, rather than doing a bunch of calculus, you could consider this as a triangle, a right triangle with a right triangular hole cut out of it. And you could save yourself doing any calculus. Whoa, this is trippy. Let's keep going here. Oh, the zombie in the canoe. You know, we might have to pick up and do a couple more problems next time. I know I'm going too fast here. So we might do this one next time and then move into chapter 10. Yeah, we've got a couple of things. So there's a few tricks we could do with center mass, and we'll maybe pick those up next time. All right, that's pretty good. So I'm going to, you know what I'll do? I'll show you a couple more codes just for fun. So if you want, this one's looking at a hemisphere, right? And so we could see inside of it there. Whoops. Whoa, oh my gosh, I'm zoomed way too. but you could get the center mass. And again, we see it's actually pretty low there. Let's go back to one. Whoops. Let's go back to here. Let's do an arc. So in this one, right, you've got to use degrees, and we've got to convert our degrees to radians here. But let's just say the initial angle, oh, let's just say this is, let's just do 90 and run it. And so this is kind of what we were, whoops, gosh, darn it. Oh my gosh, let me run it again. Okay. There we go. Sorry about that. So this is showing you that Fosbury arc. You could actually, by arcing your body, get your center mass a little bit below there. And like I said, we're gonna do some codes, and I'm gonna have you do them a little differently than these ones. These ones totally killed people. But yeah,